How many fruits pass through this belt? At full speed, with constant motion, overlap, and blur, even an experienced operator can only estimate. Manual counting breaks down the moment throughput increases. Errors creep in. Productivity slows. Data becomes unreliable. Now watch what happens when computer vision is applied. Each fruit is detected individually, even when they touch or partially occlude each other. Movement is tracked across frames, so the same object is never counted twice. A virtual counting line converts physical flow into a precise digital signal, accurate, repeatable, and real-time. This is not just about counting fruits. In manufacturing, counting is the foundation of everything that follows. Production metrics, yield analysis, inventory reconciliation, packaging validation, and downstream automation. By using computer vision on a conveyor belt, manufacturers gain continuous visibility into their process. Throughput can be measured without stopping the line. Bottlenecks become visible. Losses and miscounts are eliminated. And the same system can later be extended to grading, sorting, defect detection, or quality inspection. In this video, we'll design and implement a real-time object counting system built for real manufacturing conditions, fast conveyors, imperfect lighting, occlusions, and noise, showing how computer vision turns raw motion into reliable production data. If you enjoy our content and want to see more, don't forget to hit subscribe.
Hello everyone, welcome to this tutorial on computer vision. In this computer vision tutorial, I am going to show you how you can create an end-to-end pipeline for object counting in a conveyor belt. So for this tutorial, I am taking an example of fruits counting on a conveyor belt. So let's see our example. As you can see, this is a video of oranges passing through a conveyor belt, and our end goal is to count the accurate number of oranges passed through the conveyor belt. So let's see what will be our workflow to implement this computer vision solution. So our key workflow will be data preparation. So in this pipeline notebook, I'm going to show you how you can create data from a sample video and then use that data to fine-tune a RT-DETR model for orange detection, which is our primary object in this video. You can choose any object you like for counting, but for this example, it's the orange. And then how you can write the logic to count the object in a conveyor belt which is passing through a specific zone, and then how you can visualize this. So let's see our notebook.
Before we continue with the tutorial, answer this question and share your response in the comments.
So in first step, we have to import some libraries which are OpenCV, NumPy, Ultralytics to use RT-DETR model, then torque, then there is your matplotlib to plot some diagram, and then some libraries like typing. From there you can import dictionary, tuple, optional, and list, and pathlib, then random, and then there is your matplotlib inclined uh, to render the diagram on the notebook. So first we start by cloning this repo. I have already cloned this repo. You just have to uncomment it and run it, and it will look like this. This repo will help us to use some helper function for our data preparation. So let's see. So our first step in data preparation is extracting frames from a sample video. Like this is the video I am taking. So I want to extract some frames for our model training, on which on the extracted frame I have to annotate it first, then train our model. So to do that, I have created a function to extract random frames from a video in a folder. So you just have to give the parts to the folder, and then give the total images you want to extract, and then the our result directory, which is dataset frames, and the run as jpg quality this, and you have to just run this, and it will give you this folder which will contain your it extracted images. These are around 50 images I have extracted from this video for our model training. and then in our next step you have to annotate it. So to do that annotation, you can either go to labeler and upload your images and annotate it on a class of oranges, or you can use our uh, open source SAM3 batch inference repo to annotate auto annotate it using SAM3 model. You just have to clone this repo and use SAM3, uh, provide the dataset frames folder and the model part, and then the text prompt, which will be your classes. Like if you want to annotate an orange class, you just have to type the orange class here and run the batch inference, and then your whole image folder will be annotated in and provide you in CocoJSON format, and then you can use labeler to upload your pre-annotation and it will still look like this. So you can also do this for your annotation. So after your annotation part is done, you just have to submit your whole annotation and then go to files and select all the annotation and export it, and it will start a export job where you can download your annotation in CocoJSON format. So with this, your annotation will be done and it will look something like this. Here is your annotation of your images, which will help you in model training. So so to convert your annotation and dataset frames into model training format, you have to use our another helper function, which is Coco to YOLO converter. As you know, Ultralytics need a special way of model training, like you need to have images folder and labels folder separately. And in labels folder, you will have three folder: test, train, and val, and then each will have a folder with the same name as the image file name, but it will only contain the annotation. So here you need this kind of format for model training, and this function can help you to convert into that format. You just have to run it and it will give you this directory. Now in next step, you just cleared your GPU memory to confirm you have sufficient VRAM for model training. Now let's start our model training format process. You just have to import, which I have already done, but I am showing it how you need to do it. You have to import RT-DETR from Ultralytics, then use RT-DETR model L for your model training, as it's a very efficient model. So you just use the model dot train and then provide it with the part model dataset dot data YAML file, which is this file part. You just have to give data equal this file part, and then epochs, which is around 200, image size should be 640, batch should be 4, device should be 0 as I am using GPU, and then worker should be 1. When you start this process, you will get the runs folder. I will show you again what will look. As you can see, you will get a runs folder, and in that runs folder you will get a train, and then there is your another model training here, and you will get your train. This is the model which we have start training. I have already done this for this tutorial, so I am going to stop it. So with that, when your training is done, it will look like that. You will get your fine-tuned model called best.pt on your own dataset on the classes you have annotated. So so let's see our inference on our sample video. So to inference on a video, you just need to use our train model part in the model variable and the video part which you want to inference. Then you just have to run model.track and the video part persist equals to true, save equals to true, and these are other arguments which you need or not. You can choose that. You just have to run it. It will create a track And as you can see, our model is working great. It is detecting oranges glass in every frame. There are around 666 frames in this video. As you've seen, our inference result by model was great, and it was able to detect and track orange classes perfectly in the sample video. Now, to create the logic to count the oranges in a conveyor belt, we have to first analyze the video more clearly. So for that, I have created a function to extract and frame from the video and visualize it. So visualize some frames which are 0, 100, 200 to 500 frame. So let's see. As you can see in this video, oranges are coming towards us. So as you can see, it's a very static video, so we just need to draw a zone from where if an oranges pass, it will increase the counter by 1. So for that, we have to use this zone as a reference, where if the oranges which we are tracking pass through it, it will increase our counter by 1, as you can see. So let's see how you can draw that. I have created this helper function to draw a polygon region for uh, counting our object in that zone. So let's draw a polygon region. As you can see, this is the frame. So here, 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 here. Now this is the region from which if the oranges is passed through, it will increase our counter by 1. So let's save it. So here is your region which we have to focus on. We are going to use this region for counting our oranges if it passed through. So let's annotate it. There's another helper function. So I have already done that value. So it will look something like that. So we have to keep this zone from every frame of the video to verify if the oranges has passed through that zone or not. Now let's see our main class which will implement this fruit counter logic. So we will initialize some static values like RT-DETR model location, which we use here for detection and tracking, then region polygon, which is this region, to know if the classes if the orange class has passed to that region or not, and then and counted IDs list, or you can say set, to ensure that no other oranges has passed through here. If we are tracking this orange, it is not counted yet, and after it is passed through here, it will add its counted ID to this set for ensurety that it has been counted, and it will not count it again. So, and then there is your some core method which are going, so there is your process frame. So it will track the model, use the counting logic and visualize it. And then there is your point in polygon. So how we are going to know that if that orange is in this zone? So we are going to first detect the bounding box. Then we are going to find the centroid of that orange using the bounding box and confirm that centroid point is inside the polygon zone. So this method will help us in that. And then the count fruit method. This is the main method. So it will take the video, use the process frame method, and then give us an output video. Then there are some other helper functions like draw detection or draw counter to draw the value of counted oranges increases on the frame by frame. So let's see, there is your some other random functions like to generate random color. This will generate some color for every a specific tracking ID orange with the same color, but every other ID will have different color. Then there are some your function which we have described, like point in the polygon, get centroid, draw detection, and process frame. As you can see, it is using model.track to get every result and checking if that model has ID, model result has the ID, means tracking ID. If yes, it is uh, getting its value and drawing it on you getting it centroid and confirming that centroid is in the polygon zone, polygon region. If yes, it is drawing the detection on each frame and returning the frame here after drawing some other values like the polygon region here, and then the overlay to show the region separate from other zone of the video frame. Then there is the main function which will use all the method which we have created. Now let's run this. Now how you're going to run this, you just have to give the list of the polygon region, then initialize its an object in counter with the that region polygon, and then give it the video part. So it started. Let's see the inference. As you see in the inference, our logic was pretty good. We were first able to detect our class, which is orange, using our fine-tuned model, and then confirm if that orange class has passed through the specific zone, which we have marked in pink color, uh, and then counted that if it has passed through that zone, it will increase our counter by 1. So with that, now you know how you can create a pipeline for of object counting on a conveyor belt. You can also check out our other videos, like how you can fine tune YOLO on custom dataset, or how you can build a real-time intrusion detection, and how you can use computer vision to find speed. So let's see you on our next video.
If you'd like to explore practical resources and hands-on examples, we've created a dedicated GitHub repository. It's filled with cookbooks covering computer vision, AI agents, and more. Link is in description.